In this lecture, we proved the well-known fact that given four distinct points z sub 1, z sub 2, z sub 3, and z sub 4 on the extended complex plane, the cross ratio of z sub 1, z sub 2, z sub 3, and z sub 4 is a real number if and only if the four z sub i's all lie on a cline being either a straight line or a circle. Because the theorem is an if and only if theorem, we divide the proof into two parts. In part 1, we showed that if the z sub i's all lie on a cline, then the cross ratio of the z sub i's is a real number. In the second part, we showed that if the cross ratio of the z sub i's is real, then the z sub i's must lie on either a line or a circle. For part 1, we first suppose that the z sub i's lie on a circle. Then there are 6 permutations of z sub 2, z sub 3, and z sub 4 in relation to z sub 1. 4 of these permutations will have z sub 1 and z sub 2 adjacent to each other on the circle. The other 2 permutations will have z sub 1 and z sub 2 not adjacent to each other. We will prove that the cross ratio is a real number for 2 of these permutations, one with z sub 1 and z sub 2 adjacent to each other, and another where z sub 1 and z sub 2 are not adjacent to each other. The proofs for the other permutations are quite similar. For the first permutation, let us suppose that z sub 1, z sub 2, z sub 3, and z sub 4 are arranged in this order counterclockwise along the circle. The cross ratio of the z sub i's is equal to z sub 1 minus z sub 3 divided by z sub 1 minus z sub 4 times z sub 2 minus z sub 4 divided by z sub 2 minus z sub 3. Rearranging the factors, the cross ratio is also equal to z sub 1 minus z sub 3 divided by z sub 2 minus z sub 3 times z sub 2 minus z sub 4 divided by z sub 1 minus z sub 4. We can associate the complex number z sub 1 minus z sub 3 to the vector from z sub 3 to z sub 1, the complex number z sub 2 minus z sub 3 to the vector from z sub 3 to z sub 2, the complex number z sub 2 minus z sub 4 to the vector from z sub 4 to z sub 2, and the complex number z sub 1 minus z sub 4 to the vector from z sub 4 to z sub 1. Let theta be the smallest non-negative angle formed by the vectors z sub 1 minus z sub 3 and z sub 2 minus z sub 3. This angle is called an inscribed angle within the circle and is formed by 2 chords of the circle where the 2 chords intersect at a common endpoint. In this case, the common endpoint is the vertex of the angle, and the vertex is z sub 3. We also have the inscribed angle formed by z sub 2 minus z sub 4 and z sub 1 minus z sub 4. The 2 inscribed angles intercept the same arc, and so the inscribed angle at z sub 4 also has measure theta. And so an argument for z sub 1 minus z sub 3 divided by z sub 2 minus z sub 3 being measured clockwise from the vector z sub 2 minus z sub 3 to the vector z sub 1 minus z sub 3 is minus theta. And an argument for z sub 2 minus z sub 4 divided by z sub 1 minus z sub 4 being measured this time in the counterclockwise direction is just plain theta. And so z sub 1 minus z sub 3 divided by z sub 2 minus z sub 3 equals its absolute value times e raised to the power I times minus theta, and z sub 2 minus z sub 4 divided by z sub 1 minus z sub 4 equals its absolute value times e raised to the power I times theta. The exponents add up to 0 so that the exponentials cancel each other out, and the cross ratio is equal to its absolute value, which makes the cross ratio a real number. For the second permutation, suppose we have z sub 1, z sub 3, z sub 2, and z sub 4 go in this order counterclockwise along the circle. This time, we take a look at the inscribed quadrilateral formed by the vertices z sub 1, z sub 3, z sub 2, and z sub 4. Let the angle at z sub 3 be alpha. Alpha being measured counterclockwise is also an argument for z sub 1 minus z sub 3 divided by z sub 2 minus z sub 3. We choose alpha to be what is called the principal argument, so that alpha is non-negative and less than pi. In the same fashion, we take the angle at z sub 4, which we call beta, to be the principal argument of z sub 2 minus z sub 4 divided by z sub 1 minus z sub 4. So z sub 1 minus z sub 3 divided by z sub 2 minus z sub 3 equals its absolute value times e raised to the power I times alpha. and z sub 2 minus z sub 4 divided by z sub 1 minus z sub 4 equals its absolute value times e raised to the power I times beta. And so an argument for the cross ratio is alpha plus beta. It is a known geometric fact that the opposite angles of a quadrilateral that is inscribed in a circle are supplementary, and so alpha and beta must add up to pi. E raised to the power I times pi equals cosine pi plus I times sine pi. Cosine pi is minus 1. Sine pi is 0, so that e raised to the power I times pi is minus 1. Therefore, the cross ratio equals its absolute value times negative 1, so that the cross ratio is real. The proof for each of the other permutations is very similar, and we conclude that if the z sub i's are distinct points on a circle, then the cross ratio of the z sub i's is a real number. Now suppose that the z sub i's all lie on a line. We first consider the possibility that one of the z sub i's is the point at infinity. Without loss of generality, suppose z sub 1 is infinity. If we replace z sub 1 by z and let z tend to infinity, z minus z sub 3 divided by z minus z sub 4 will tend to 1 as z tends to infinity, so that the cross ratio of the z sub i's is equal to z sub 2 minus z sub 4 divided by z sub 2 minus z sub 3. Since the z sub i's are all collinear, then an argument of z sub 2 minus z sub 4 divided by z sub 2 minus z sub 3 is either 0 or pi. And so z sub 2 minus z sub 4 divided by z sub 2 minus z sub 3 will be equal to its absolute value times either e raised to the power I times 0, which is equal to 1, or e raised to the power I times pi, which is equal to minus 1. And so the cross ratio will be equal to plus or minus its absolute value, so that the cross ratio is a real number. The proof is quite similar if the z sub i's are all finite and collinear. If all the z sub i's are finite and collinear, we can set the argument of z sub 1 minus z sub 3 divided by z sub 1 minus z sub 4 as either 0 or pi. We can do the same for the argument of z sub 2 minus z sub 4 divided by z sub 2 minus z sub 3. Therefore, an argument of the cross ratio being the sum of these two arguments will be an integer multiple of pi, so that the cross ratio should be equal to its absolute value times e raised to the power I times n times pi, where n is some integer. E raised to the power I times n times pi equals cosine n times pi, which is plus or minus 1, plus I times sine n times pi, which is 0, so that e raised to the power I times n times pi is plus or minus 1. Therefore, the cross ratio is plus or minus its absolute value, which makes it a real number, completing the first part of the proof. We now prove the second half of the theorem. Suppose that the cross ratio of the z sub i's is a real number. Let the cross ratio be equal to some real number r, which we can assume is non-zero since the z sub i's are all distinct. There is a unique Möbius transformation that we will call f, such that f of z sub 2 equals 1, f of z sub 3 equals 0, and f of z sub 4 equals infinity. For a proof of the existence and uniqueness of this Möbius transformation, we refer the viewer to the video Möbius Transformations, Existence and Uniqueness of Mappings. We are including a link to this video in the description of this lecture. The viewer can also check that f of z can be written as z minus z sub 3 divided by z minus z sub 4 times z sub 2 minus z sub 4 divided by z sub 2 minus z sub 3. Observe that f of z sub 1 is equal to the cross ratio of the z sub i's, which is equal to the real number r, so that f of z sub 1 must be a real number and therefore must lie on the real axis along with 1, 0, and infinity. The real axis is also a cline. It is also known that every Möbius transformation maps a cline onto another cline. The viewer can check the video Möbius transformations, lines, and circles for a proof of this fact. F inverse is also a Möbius transformation and will map the real axis, which is itself a cline, onto another cline. Let's call this cline C. Cline C will contain F inverse of R, which is Z sub 1, F inverse of 1, which is Z sub 2, F inverse of 0, which is Z sub 3, and F inverse of infinity, which is Z sub 4, so that the Z sub i's all lie either on a line or a circle. Therefore, if Z sub 1, Z sub 2, Z sub 3, and Z sub 4 are distinct points on the extended complex plane, their cross ratio is a real number if and only if the Z sub i's all lie on either a line or a circle.